Okay, so you want to look at a normal distribution. A normal distribution is a continuous random variable, and the PDF of this particular continuous random variable, a normal distribution, has this sort of bell-shaped curve, right? Okay, so what we will eventually get to is you want to calculate probability of your normal distribution lying between two values in an interval like this, right? And that corresponds to the shaded area over here, right? Which is standard theory for a continuous random variable. Um, we're not going to use a PDF, we would eventually use a table. Anyway, so before we get into this normal distribution, what I want to do is I want to do a little review. So do a quick review of discrete, then discrete random variables, then do a review of continuous, right? And then we will move on to what we need to talk about, which is normal distribution. Okay, so reviewing over here discrete random variables, right? So I'll use the simple example that we saw already, right? That's in the course notes, of course. Right, so we have an experiment where we flip a fair coin twice, right? And your sample space is going to have four outcomes, right? So if you flip your coin twice, you can get two heads, you can get a head or a tail and a head, and then, or you can get two tails, right? Okay, so these outcomes, because the coin is fair, right? Each of these outcomes is equally likely, right? And that would mean that the probability of each one occurring is a quarter, right? Anyway, so this is your sample space associated with this experiment, right? Your random variable, we talked about this. This is random variable is a function on the sample space, right? That is a somewhat sort of technical way of probably looking at it, right? Usually a random variable associated to experiment is usually stated in some sort of like English format like this, right? Okay, so in this case, the random variable is the number of heads that you get when you perform this experiment. Okay, so the number of heads that you can possibly get, right? You can actually see it right here from your sample space, right? You can get, say, no heads at all, so zero heads, right? Or you can get one head over here, so that's these two cases, or you can get two heads, right? Right, so your possible values of your random variable x over here, uh, 0, 1, and 2, right? Okay. Right, so that's the main thing that I really want to get to review in this discrete random variables is the point that if you have a discrete random variable, what's going to happen is that the possible cases, the possible values for your random variable are discrete like this, right? 0, 1, 2, right? So it's not continuous or anything like that. You're not going to have, say, like 1/3 or a quarter or something living between the 0 and 1, right? You have 0, 1, 2, and so on, right? Okay, with each of these over here, for example, like x is equal to 1, if you want the probability of x is equal to 1, well, seeing that we're here already, right? Probability of x is equal to 1 means that you're gonna, it means that the probability x is equal to 1 is probability that you get exactly one head, right? And the cases of one head would be these two over here, right? Okay. So probability of x is equal to 1 is the probability of falling into one of these two cases. Each of these has probability a quarter, so the probability x is equal to 1 is quarter plus a quarter, which is a half. Right? Okay, so you can work out the probabilities for each of the cases. So your possible values of the x would be 0, 1, and 2. We just saw that probability x is equal to 1 is a half. And similarly, you could work out probability x is equal to 0 as a quarter and probability x is equal to 2 as a quarter, right? Okay, so this is an example of a probability mass function, right, for a discrete random variable, right? When we get to the continuous case, it's something like this, but it's not going to be identical, right? So in the case of a continuous random variable, what you're going to have is a probability density function, not a probability mass function. All right, okay, so remember what we want to do, right? We want to eventually get normal distribution, which is a continuous random variable, right? So I'm still doing a little review over here, right? So let's look at a case of a continuous random variable, and this sort of simple case over here, it is a continuous uniform distribution, right? So what this is in your general case over here, it's a random variable that is really just going to take values between A and B over here, right? And the probability that it takes any value between A and B is actually the same, right? Okay, and that is indicated by the fact that the PDF over here, so the probability density function, is in fact flat, right? For your values between A and B, right? So the idea over here is that between A and B, you have this constant density function, right? And outside of A and B, right? So on this side, your probability is 0, and on this side over here, your probability is 0, right? Okay, something having a continuous uniform distribution is denoted like this over here, right? So this tilde over here is meant to indicate that your random variable has a certain type of distribution, and the big U is supposed to stand for uniform. And remember, we're taking values between A and B, so that's what this A and B are about over here, right? Okay. Right. Okay, so we did this theory already. If you guys were coming to class, you would have heard me talk about this, right? Anyway, right. So let's look at this particular example of uh, continuous uniform distribution, right? Okay, so we have this meeting that's occurring in a specific conference room, right? And the length of the meeting, so the length of time of the meeting, right, is given as having a continuous uniform distribution, which on the interval 0 to 4, right? Okay, so what this means is that the length of your meeting can go have any length between 0 over here and 4 over here, right? And the units, well, hours, right? So between 0 hours and 4 hours, right? Okay, probably it's not realistic, but that's just what is given to you in your problem, right? Okay, and what we want to do is we want to get the probability that the meeting lasts more than 3 hours. Okay, so that is the question over here, right? I mean, this is the answer, but I sketched out probably a better answer over here, right? Okay, so if you're doing this sort of problem, these types of problems, right, first thing you probably want to do is you want to identify what is your random variable, right? So your random variable over here is the length of time of the meeting, right? So we're going to call that big X here, right? Okay, and this big X over here, we're told that it has a continuous uniform distribution, right? So big X has this continuous uniform distribution on an interval 0 to 4, right? Okay, so what that means, this is what the PDF, okay, so the PDF of the random variable X over here, so PDF is the f of X, right? And the graph of your PDF is going to look like this, right? So as I said, the length of the meeting is going to be between 0 and 4, right? The fact that this is flat over here like this, the PDF is flat like this, means that you're equally likely to take any value between 0 and 4, right? And the fact that it's 0 on this side and 0 on this side, for example, 0 on this side means that the length of the meeting is not going to be less than 0, right? And the length of the meeting is not going to be larger than 4. Right? So this is your PDF over here, and you could actually, this is in graph form over here, but you could write it, I'm missing curly bracket over here, you could write it as a piecewise defined function, right, where the f of x is going to be a quarter between 0 and 4, right? Okay, so where this quarter comes from is that, remember that your probabilities is supposed to essentially add to 1, right? So if you integrate this between 0 and 4, right? Well, actually, if you integrate straight through, right, from minus infinity to infinity, what you're supposed to do is supposed to get 1, right? When you're integrating from minus infinity to infinity, right? Really, because it's 0 on this side and 0 on this side, just means that the only thing non-negative over here that you're actually integrating is between 0 and 4. So basically, when you integrate from 0 to 4, you're supposed to get 1, which means that this area over here is supposed to be 1, and if this length here is 4, then this height has to be a quarter in order for this area here to be 1. Anyway, right? So that's a quarter there. Okay, so your PDF is this over here, right? Which is the same thing illustrated in the graph. What they ask us to do is they ask us to get the probability that x is, well, they ask us over here, right? The probability that the meeting is going to last more than 3 hours, right? So we want a probability that the length of time of the meeting, which is x, is going to be bigger than 3. Okay, so probability, you want probability x is bigger than 3. I state it in this way over here because I want two sides. I want it two-sided so I can put in the limits for my integration over here. And the point, I guess, that I really wanted to get to for this continuous case is when you have a probability, right, for interval like this, right, how you're going to work it out in the continuous case is by integrating a PDF, right? So the PDF is a small f, and so you integrate your PDF between these limit values, right? Which in this case is 3 and infinity, right? So once you set this up, now you need to do this integration. Okay, so if you're doing this integration, what you're doing is you're integrating from 3 over here to infinity, right? So from 3 here, and you keep going until you get to infinity. Right, now you want to notice that you have a different type of behavior from 3 to 4 than you have from 4 onward. So you split it up over here. So you integrate from 3 to 4 and then 4 to infinity. Right, between 3 and 4, your PDF is equal to a quarter. You're seeing it over there in the graph. Okay, and then from 4 onward, it's equal to 0. Right? Right, so here you're integrating a quarter, here you're integrating 0. This over here will just drop off here to 0. And all you need to do is integrate that. That is straightforward. You integrate a quarter with respect to x, you get x on the 4. You put in your 4 and your 3 and you get the answer over here, right? So probability x bigger than 3 is a quarter, right? And if you sort of reason, you could actually reason this out logically over here in this particular case because uniform is so simple, right? And it's flat like this. You could probably reason out that, well, alright, if the possible values are going to lie between 0 and 4 and you want probability x bigger than 3, right? It means that the length of the meeting could only be between 3 and 4 now, right? So you have a length over here one of 1 where your total possibilities is 4, right? So your answer is going to turn out to be 1 on 4, something to that effect. Alright, okay, so we get to normal distribution, which is what we wanted to talk about. Okay, so normal distribution is a continuous random variable, right? Okay, so it's a continuous random variable. This notation x over here, remember your tilde means that it has a certain type of distribution, and the n over here is supposed to mean normal, right? Your normal random variable, the mean is denoted as mu over here, and well, the standard deviation is sigma, right? And remember, variance is standard deviation squared, so the variance is sigma squared over here, right? All right, so I guess first thing you want to get out of this uh, random variable that has a normal distribution is that the PDF is gonna have a bell shape, right? So the simplest case, I guess, more general case over here is you see in the PDF of x over here, right, will have this sort of bell shape. If I drew this extremely accurately, this green over here needs to keep going like this. So this would be a horizontal asymptote over here. And this would need to keep going like this and basically get closer and closer to the x-axis as you go along, right? Okay, so normal distribution has this sort of bell shape. If it is normal distribution, this sort of general case, the mu over here is where your normal distribution is centered, right? And the sigma is giving you an idea of the dispersion about this mean over here, right? So mu plus sigma would be, say, like somewhere over here, and then mu minus sigma would be over here, right? Okay, so next thing you want to realize is that this normal distribution is symmetric about your mean mu over here, right? So what that means is, well, it's symmetric, right? If you reflect, right, this half in this vertical line over here, you're gonna get that side. All right. Okay. All right. So your normal distribution is bell shaped like this over here, right? The All right. So your normal distribution is particularly important. The uniform distribution that we looked at before, right, was, I mean, it isn't bad, but it isn't nowhere as important as normal, right? And normal is also called a Gaussian, right? But in this class, we'll just refer to it as normal distribution, right? Okay, and we'll see later on, for example, with like a central limit theorem and your statistical distributions and so, right? Normal distribution is used extensively, right? So it is pretty important, right? And being able to calculate probabilities for normal distribution, well, you need to know how to do it. Okay, right. So your normal distribution has this particular PDF over here, right? And the PDF over here, what you want to do is you want to realize it. You use an exponential over here, right? And while it may look a little complicated, right? You To sort of understand what's going on over here is you really should sort of consider this kind of case over here, right? Okay, so here what I have is an exponential. It's not your normal exponential where it's say like e to the x or something like that. If I hide that minus sign and I hide the square over there, right? It's e to the minus x squared, right? And this sort of graph of e to the minus x squared, well, the fact that you have the x squared over here is going to give you this symmetry about your y-axis here, right? And the negative over here will cause you to drop down like this, right? And the fact that it's negative and x squared means that if you're on this side over here, say if you're at minus 2, right, then minus 2 squared is 4, right? So that would make it positive, and then you put an x minus over here. So what you'd end up with is negative values feeding in over here, right? Like on this side. So again, this side you just drop off to 0, right? Okay, so this is your basic shape of e to the minus x squared, and this over here is pretty close to what a standard normal is going to look like, but we'll get to that. Right. Anyway, so uh, from this over here, what you can do is you can get an idea of what this general case is going to look like, right? So this is x squared over here, right? What you're doing is you're going from x squared to x minus mu squared for the time being. And what that does for you is it gives you a translation, right? So the mean over here is 0 over here. And having the x minus mu will cause you to shift by mu to the right. Okay, so yeah, 0 over here will shift this way. And now the mean is now centered at mu, right? Okay, what the sigma does for you, right, is the sigma will scale, right? Okay, so if you notice over here how I drew this had a certain sort of like shape over here or spread, right? And this over here is narrower, right? So what the sigma does for you is it either compresses or expands, right? Depending on if the sigma is bigger than or less than 1, right? Okay, so let's look at say a couple cases of what the PDFs of a normal distribution would look like, right? Okay, so if we look over here, right, so these are two different, this is one random variable, right, with this normal distribution. Second random variable with this normal distribution, right, and I drew the graphs of each PDF, right, of both PDFs on the same plot here, right. Okay. All right, so you want to notice the x1, the PDF for the x1, the mean is 5 and the standard deviation is 4, 2 squared. And for this one over here, the mean is 10 and the standard deviation is also 4, right? So they have the same standard deviation, right? So if you look at this one over here and you look at how it's spread about the mean over here and the spread and then the spread for the x2 is actually the same about the mean of 10, right? So that's the difference in the standard deviation. Well, not the difference, the standard deviation is exactly the same for both of them. So it means that the spread about the mean is the same for both of them, right? The means, however, are different, right? So this one has mean 5, right? And this one has a different mean, so it's centered about 10, right? But as I said, the overall sort of shape, right? Once so the mean would sort of lock it in place if you want, right? And then once you start to look at the spread of it, or if it's narrower, if it's wide, right? That depends on the standard deviation or variance over here. And it's actually the same for both of them, so they both have the same sort of shape about the mean, right? Right. Okay, so this guy on this example over here, again, what we have two random variables, right? Both normally distributed. In this case, the mean is 5 for this one and 5 for this one, so they have the same mean, right? So x1 has mean 5, so this is your x1 over here, and the mean over here is 5, so it's centered about 5. The x3 over here also has mean 5, it's centered about 5, but now they have different variances, right? Okay, so your larger variance over here of 4 means that you're going to have a wider spread like this over here. So the x1 with the larger variance has wider spread over here. The x3 with the smaller variance over here of a quarter, right? The dispersion about the mean is smaller, right? And dispersion about the mean being smaller means that if you look at the PDF is going to be narrow like this over here, right? Okay, all right. So now what you want to do is you want to get probabilities for this normal distribution, which is probabilities. Normal distribution is continuous, so the method of getting your probabilities would be, in a sense, should be the same, right? For any continuous random variable. So you want to remember if you have a continuous random variable, and this is a general case, any continuous random variable with a PDF, right, specified by f of x, then the probability of the random variable line taking values between a and b is given by this integral, right? So integrate your PDF over here f of x between a and b, right? Okay, so x is a continuous random variable with this PDF over here, right? Okay, so what that means is that if you want to get for your random variable and you wanted to use this sort of integration formula, this you'd put your PDF over here with the exponential, right? And the x minus mu squared and the sigma squared down there, right? And if you're going to just do it directly like this, then if you wanted to get the probability of your random variable taking values between x1 and x2, right? You need to work out this integral here, right? Okay, so intuitively, what it means is this is your PDF over here, right? So the PDF of the normal distribution, which is the exponential times this factor over here. This is your PDF. And getting the probability that you lie between x1 and x2, right? Remember what you're doing is you're integrating between x1 and x2, which means that you're getting this area over here, right? So intuitively what you're trying to do is when you're calculating a probability for a normal distribution for your bell shape over here, what you're trying to do is you're trying to get an area under the curve between your x1 here and your x2 over here, right? Wouldn't always be this exact sort of setup over here, but usually, okay, so it could be different like this over here, right? But anyway, right, so the point that I want to make here is that if you're going to do it this way and you're going to try to integrate this integral, is there's no closed form for it, as far as I know, right? In other words, there's no sort of formula. You won't be able to integrate it and substitute the values, right? So something like this, you need to either you work it out numerically using a computer, or the way that we're going to do it is you're going to use tables, right? Okay, all right. All right. Okay, so to calculate your probabilities for a normal distribution, right? You cannot use this formula over here directly, right? So what we're going to do is you're going to use a table, right? Now, the thing about this is, well, if you're going to use a table, right? If you look at this over here, right? You have, well, mu could be anything, right? And sigma could be anything, right? And well, this is what your table is going to be like over here, right? Now, if the mu and sigma could be anything that you wanted, right? Then what you need to have is, well, you need to have a very large or infinite number of tables, right? So you don't want, in order to use your table and so, right? What you need to do is, first of all, you would need to convert this over here, right? You want to standardize, right? So the standardization is actually a substitution, right, that we will eventually get to, right? But when you using this over here and you want to calculate a probability for a normal distribution, the first thing that we're going to do is you're going to convert, right, z. So this over here, you're going to convert to standard normal. So this is your PDF over here for your general case, right? So normally distributed, if x is normally distributed, this is your PDF for normal case over here, right? And by standardizing, what I mean is you're gonna use some sort of substitution where eventually you're gonna reduce down to the case when the mu is equal to 0 and the sigma is equal to 1, right? Okay, so what's gonna happen over here is when you do that, you're going to get the mu is going to go to 0, this sigma is going to go to 1, right? And part of the conversion, because it's a substitution, right, is the substitution that you're going to use is this over here. Right? I will explain this a little more because the conversion takes a little bit of work, right? Okay, so this is a substitution that we're going to use that will take us, so it'll get rid of the mu and the sigma, right? And that will do the conversion from a general case, which is over here, right, to this case over here. Right? Okay, so point I want to make is that if I have an x normally distributed in a normal sense with a mean mu and sigma squared, eventually what I'd want to do is I want to calculate these sorts of probabilities over here, right? Probability of x lying between x1 and x2. Okay, I can't do it from an integral. I'm going to have to use a table, right? And in order to use a table, I will need to do a conversion to standard normal, right? And when you convert to standard normal, it is standard normal. So it is a normal, right? A standard normal is denoted as z, right? And when you do the conversion, what you do is, well, it's a change of variables, right? And conversion will take you, so this is the original one over here, right? And conversion will take you to this over here, right? So if you want to notice, the form is the same. Well, the form is similar, right? Okay, here it's z squared and here it's x minus mu squared. Okay, so this over here is what you get by letting mu equal to 0, sigma equal to 1, and you're doing conversion, right? So the x will change to z, right? Okay, right. So given this over here, this would be how you would convert, right? We will talk about this later on, right? I will talk about how you're going to get this conversion over here, but for the time being, we want to calculate values, as I said, right? Anyway, so since already here, right, this is how you would do the standardization, the conversion. So this is what you'd have to start off with, and once you do your standardization or you do your conversion over here, the z is also going to be normally distributed, right? Where the mean now is going to be 0 because you're subtracting off the mean over here, and the standard deviation is going to be 1 because you're dividing it off over here, right? Right. Okay, so we if you want to calculate probabilities for normal distribution, you need to convert to standard normal. So what we want to focus on right now is calculating probabilities for standard normal, right? Okay, so the easiest one to calculate is if you're calculating probabilities for standard normal that look like this, right? So what you want is probability that is standard normal is bigger than some value small z over here, and that small z is given to you somehow, right? Okay, so why this is the easiest case over here, right, is because this calculating something like this over here is just going to come directly from the table, right? Notice over here, here I have a right hand tail, so a right tail over here, and here I also have a right tail. This would be the form of the table that we're going to use in the exam, right? There are tables where you're gonna have, say, probably the left tail given to you, or you'll be given this side over here, right? You probably don't want to get too used to using those tables because in the end, this is what will be given to you in either your midterm, well, in your midterm or your final, or the assessment that would probably replace your midterm. Okay, so we want to calculate probabilities for standard normals, and we're going to be using tables like this over here, right? Okay, right. So let's start calculating probabilities for standard normal, right? So we want to determine this probability over here for this standard normal distribution, right? So z bigger than 1.25, right? And as I said, this is about the easiest case that you have, right? Now, when you're doing these, it doesn't hurt to draw, say, like a small diagram to see what's going on, right? So you draw a standard normal, which is standard normal over here is going to have a bell shape because it's a normal distribution. Your mean is equal to 0, right? For the purposes of graphing, doesn't really make a difference, right? How you graph this sort of spread. Well, at least over here, right? Anyway. Okay, so we want probability z bigger than 1.25, right? So we put the 1.25 over here. And what we want is probability z bigger than 1.25. Okay, right? So what that means is we want the area under the curve between 1.25 and infinity, right? So what we want is we want this area over here that's shaded in red, right? Now this area shaded in red is basically just going to come from your table, right? So we want probability z bigger than 1.25, and this is just using this table over here, right? So what you do is you first use your column over here, right? This 1.25, you're trying to locate it on your table, right? Okay, so your 1.2, you 1.25, you have your 1.2 over here, right? And what you do is you're using this row over here on top to fine tune, right? So you have 1.2, right? This would be, say, like corresponding for 1.21, right? So on. But what we want is for 1.25, right? So this is 1.2, right? Plus 0.05, which would give me 1.25, right? So your probability for z being bigger than equal to 1.25, the probabilities, these shaded areas are given over inside here, right? And for 1.25, the probability is this guy over here, which is the 0.1056. So that's how you get this, right? Okay. So your tables over here, these probability values are probabilities that take this sort of form here, z bigger than this, right? The form is important, as we will see, right? Right. Okay, so now let's take a look at this one over here, right? We want probability of z less than 1.25, right? Now, what you want to notice is that this is not going to come directly from this table over here, right? Because for z less than 1.25, again, what you should do is you should draw a sketch, right? And indicate this probability by an area under the curve, right? Right, so how you draw your sketch is you draw your standard bell shape over here, right? You put your 1.25 in as it is across here. But now that you want z less than 1.25, we're looking at this shaded area, right, to the left over here, right? Right. Okay, so we want the probability of z less than 1.25. In other words, somehow we want to get this area over here, right? Okay, so how do we do that? Well, how you're doing that is that you using the fact that this red area over here plus this blue area over here, this is going to be equal to 1, right? So this is what I have stated over here. Slight difference over here to be like technically correct, and so right, I'm actually including the 1.25. So probability z less than equal to 1.25, right? So this red area including the line over here, and then the probability z bigger than 1.25, which is the blue area over here, right? I can write it like this if you want. So z less than equal to 1.25 is between minus z line between minus infinity and 1.25, and the z being bigger than 1.25 is z bigger than 1.25 but is z less than infinity, right? Now these over here, what you could do is you could merge the endpoints over here since they match, and what you're doing is this would be when you add in these probabilities over here, what you're doing is you're getting probability from minus infinity to infinity, and for any continuous random variable, probability between minus infinity to infinity is always equal to 1, right? So if you want, that's a little justification for the fact that this red area over here and this blue area over here has to be equal. When you sum them, it has to be equal to 1, right? Okay. Or if you want it similar to having probability A plus probability A complement is equal to 1, which we saw before. Right. Okay, so once we have this, right, what that tells me is I want to get probability z less than 1.25, right? This is what I'm asked for, right? That is actually equal probability z less than equal to 1.25 because including the equal signs is not going to make a difference. We talked about this in class. This is essentially because this case over here, you could actually split into this case over here on the right hand side. You could split into this case plus probability z is identically equal to 1.25, and the probability of a random variable, continuous random variable being exactly equal to value is actually 0, right? We talked about that before. I will briefly mention that in a second, right? Anyway, so in the case of a continuous random variable, it doesn't make a difference if you have the less than or equal to is actually the same, right? And the point is, now that I have my less than or equal to, right, I can use what I had before over here, right? So the less than or equal to is going to be 1 minus this over here. So I have 1 minus this, right? Now you don't need, this is a justification of me explaining, right? If you're doing this other question, it is okay if you say that this over here is equal to 1 minus this expression, right? Okay. Right, so the point is the z less than 1.25 is now expressed as 1 minus probability z bigger than 1.25, and this over here is something of the form that is going to come from a table, right? It's going to come from the table, right? And we actually worked it out already. So probability z bigger than 1.25, again from the table, what you do is you come on the side over here first, use the column, right? 1.2, and then you fine tune using a row over here. So 1.2, and then with the 0.05 you come down to over here, right? So that gives you this. So you get 1 minus this expression, which is the 0.8944, right? Okay. Okay, right, so we continue in calculating probabilities for standard normal, right? Right, so what we saw in, let's just recap a little bit, right? This is the easiest case to calculate because this is just going to come directly from the table, right? Okay, this over here, right, where it's now less than, right? This, and again for all of these you should draw a diagram, right? So this one over here is not going to come from the table, but when you draw a diagram like this, right, what you'd realize is the probability z less than 1.25 is 1 minus this over here, right? So the red is 1 minus the blue, right? And then this over here is of the form that you want, and you can get it from the table, right? Okay, so the thing about doing these sorts of problems is basically you're trying to manipulate this, use either that sort of complement formula or use some symmetry, which you're going to talk about now, to basically always get down to something that looks like this, right? All right. Okay, so now this case over here, right? So this case over here, what I want now is probability z less than negative 1.25, right? Now, again, what you do is a good idea to draw this, right? So I have draw my standard normal, right? I have the minus 1.25 over here. I can draw that over there. And I actually just go ahead and draw plus 1.25, right? And notice you have your symmetry over here, right? Now what I want is probability z less than this negative minus 1.25, so I want this blue area over here, right? And what you want to notice is that this blue area over here by symmetry, right? This is e to the minus z squared. This is going to be symmetrical about this y-axis over here. So that symmetry would imply that your blue area over here is equal to your red area over here, right? Um, so if you want to calculate this, all you need to do is just calculate this. This is equal to this, right? So probability z less than minus 1.25 is equal to your red area, which is probability z bigger than 1.25, and now this comes from the table, right? The 1.2 and then the 0.05, right? And it gets you this over here. Okay, right. So both your examples that we just did, right? So the example that we did, which was this one over here, z less than 1.25, right? And here we have z less than minus 1.25. Both of these, notice these are z less than, right? So we could actually write up a little formula for this case of z less than something, right? If z is less than something, there's two ways to do it, right? One way, and the two ways to do it depends whether when I have z less than, right, whether the z, what I have over here, if it's positive over here or if it's negative over here, right? If it's positive over here and it's z less than, right, then you need to do this business with the 1 minus, right, which is what this formula is saying, right? Okay. So if I want probability z less than z and I'm dealing with something that is non-negative over here, right? Right, so either 0 or positive, then I'm going to use the 1 minus like across here, right? So if it is non-negative, then probability z less than something that is non-negative, then it's 1 minus probability z bigger than over here, right? So that gives me this case here. And if it's probability z less than something that is negative, then what you're doing now is you're using the symmetry, right? So the probability, in the case of when z is negative, if I want z less than a negative value over here, so negative value, then what you're doing is you using, instead with the minus 1.25, what you want to do is you want to take a positive value, right? But if this is negative, what you could do is you could hit it with a next negative sign, and that would make it positive, right? So if this is negative, you hit it with a next negative sign over here to make it positive, right? So if this is negative, then the minus z is going to be positive. And really you're in this sort of case over here, right? So that is what this second one does for you. Okay, so we're going through these cases of calculating probabilities with for your standard normals, right? And now what we want to do is we want to look at our next case, right? I'll do this in a more sort of general setting, right? Not as an example, but just using variables, right? Okay, so what I want now is probability. Now this z over here is negative, right? And I want the probability that this standard normal is bigger than a negative value, right? So I'm looking at a z over here, right? So this is a z that's given to me. And that z over here, it is negative, right? So it means that it's on this left-hand side of your z-axis, right? Okay, so what I want is probability z bigger than this negative value, right? So probability of z bigger than this negative value is this red area over here, right? Now it's z bigger than, right? And it may seem that it's sort of like this over here, right? So you're looking, this is probability z bigger than. So you have something on the right hand side. But the problem with this over here, this is not going to come from the table, because if you notice, this z over here for the table, right? This z is only up to okay, so for this table over here, right, you want to notice that your z over here is never takes, the small z over here is never going to take any negative values, right? So if you calculate in probability big z bigger than the small z, right, your small z for the table is either 0 or values bigger than 0 for the table, right? So if we're working this out, when the want to work out in a case when the z is negative, you can't use your table directly, right? So you need to use a little bit of manipulation, right? Okay, so your manipulation is this over here, right? Again, it's always a good idea to draw a diagram like this to see what's going on. We want probability of the big Z being equal to this negative value. So what we want is this red area, right? Okay, so how you're gonna do this one is you're gonna do this use complement or the one minus business, right? Okay, so probability of this Z bigger than small z, right, is, so that's equal to this red area, and this red area is 1 minus this blue area over here, right? Okay, so red area here, which is this one, is 1 minus your blue area, which is this one, right? And again, you had that small technicality with the less than or equal to, right? But you could always, as I said, right, it doesn't make a difference in the continuous case, because this value over here, this probability is equal to this probability over here, right? So if you're doing this example, you could just say that your red area over here, right, which is this one, is 1 minus your blue area over here, and then you could use a strictly less than over here, right? Now this is z less than a negative value over here, and when you have probability z less than a negative value, right, that is actually like this case over here. So if you have probability z less than a negative value, z less than, and this value is negative, how you do that is from this case from before, right? Now z less than, you convert that to z bigger than, and you convert your negative over here to positive, right? So that is what going from z to minus z will do for you, right? Remember that this is negative, and now minus z is going to be positive, right? So you could take that as a formula for this case over here. If z is negative, right, and we want probability of if small z is negative, and we want the probability that your random variable is bigger than this small negative z over here, how you do it is you use this here, right? And this is 1 minus probability z bigger than a positive value over here, and this over here is going to come from a table, right? Okay, all right. So again, looking at probabilities for standard normals, but now what we have is we have this two-sided interval over here, right? Okay, so previously what we had was one-sided, like this over here, right? Now we have two-sided, right? And the idea over here is that basically, well, you're going to split it up into two one-sided cases, right? Okay, so again, with these over here, it's usually a good idea to just do a little sketch, right? So I have standard normal, right, which is normal distribution centered at 0, right? I put in the negative. In this case, I have minus 0.38, so that's on the side. In this case over here, I have 1.25, which is on the side. What I'm looking for is standard normal line between these two values over here. So what I'm looking at is I want to get this red area over here, right? So this red area is equal to this probability, which is what I want. Okay. Now, this is your red area, and this blue area over here, and this next blue area, right? If you look at that, this blue area, this red area, and this blue area consists of your total area under the curve. Your total area under the curve is equal to 1, right? So that means that this blue area, which is equal to this probability, this red area, which is the probability that we want to determine, and this blue area, this right tail, is this probability that is equal to 1, right? Okay, so what we could do is we could solve for what we want, right? We take both of these two, this one on this end and this one on this end, and move it across to the right hand side, which is what this is over here. And now what you have is you have these cases, right? Now these cases over here are both one-sided, right? And we saw how to do those already, right? The z bigger than 1.25, that's just going to come directly from the table, right? The 1.25 is just going to come directly from the table, and this over here is probability z. This one over here is z less than a negative value, right? Now z less than a negative value, you want to remember how we do that one, right? How you do that one is, if we have something less than a negative value, what you want to do is you want to use your symmetry over here, right? So z less than a negative value is going to be equal to probability z bigger than the positive value. So notice this negative over here, convert to positive. So you do the same, use the same idea over here. And now both of these are just going to come straight from a table, right? Right. So let's actually pull this one from the table as well to get a little practice with the table. Right, so what I have is 0.38, right? So I have 0.3, right? And then I fine tune it with the 0.08 over here. So I have 0.3 with the plus the 0.08 to give me 0.38, right? Which is the 0.352. So this is the probability over here, and that goes there, right? And then finally you just work that out. Then this probability is your required probability, right? Okay.